Hello everyone, my name is Hao FU. Today I'm glad to present our work, DVQShare, an analytic system for DNN-based video queries. This paper is a joint work with colleagues at Tianjin University and Nankai University. Video cameras and DNN-based video analytic applications are pervasive today. They can be used in traffic control, public security, work safety, and video search. For example, we can use surveillance cameras to fight against crimes or ensure safety production in factories and construction sites. So let's look at some traits in these applications. First, there is a quest towards getting higher result accuracy, but this always comes with a higher processing cost. From the right picture, you can find that as the average of network models drops, the processing time of one video frame with GPUs keeps going higher and higher. Another trait is that a video analytic system often needs to process multiple queries concurrently. As the amount of video contents exposed and the number of users increases, many works have been done to accelerate the processing of DNN-based video queries. A typical video analytic application can be formulated as a processing pipeline, as shown in this picture. This pipeline composes of three phases, including pre-processing, DNN-based analysis, and post-processing. Input video data will be first decoded into frames. Then these frames will be transformed to meet the input requirement of neural networks and resampled to remove similar frames. After that, DNN models will process all frames left. The corresponding results will be processed before return. Since consecutive frames often have similarities in their contents, a straightforward method is to reduce the number of frames to be analyzed by resampling. GRIMS is a specific hardware solution which gives variable vision using low-power vision modalities. Another is the software-based solution. NoScope and FSVA adopts a method based on the difference measurement of two frames. A predefined threshold is used to determine whether the current frame should be analyzed with network models. Besides, a cascade model design is exploited to reduce the number of calls to the ground truth model. However, this works only focus on optimizing the performance of a single analytic pipeline. Some other works tend to adjust the pipeline configuration to achieve better overall performance. There are many configurable knobs in the processing pipeline, such as resolution, model selection, and frame sample rate. Different knob combinations have difference in result accuracies and the requirements for computing resources. To achieve better performance with the same computing resources, video storm can adjust resource allocations of multiple queries processing pipelines. Commining is another related work which periodically adjusts the configuration of a long-time query by considering the cross-camera correlation and the independence of configurations. Even these works have done some excellent jobs to optimize the processing performance of a video analytical system. In these works, multiple queries are still processed separately. In summary, wireless cellular relationships across queries have been largely neglected in most prior works when optimizing the system's processing performance. Next, we will use some examples to show why these sharing relationships can help us reduce the overall processing time. In this paper, we focus on two main kinds of video queries which are considered in many works. The first one is the limit query, which means that we want to request all frames and a user-defined quantity limitation on a specific target object. Another one is recognition query. This kind of query is used to request frames with a specific person or a given object. Considering the following two video analytic queries, at time t1, U1 submit Q1 to the analytic system. We suppose that it costs 10 minutes to process this query. Later, U2 submit the same request at time t2. Conventionally, the system will treat U2's request as a separate task. Hence, it costs another 10 minutes to process it. Obviously, we can cache results of U1's request to accelerate the processing of U2. We call this temporal sharing in this paper, which is typically useful when many users are interested in the same hot video clip. In the second example, the system receives Q1 requests from U1 and U2. U1 focuses on a video clip ranges from 10 minutes to 20 minutes, and U2 want to analyze frames between 15 minutes and 25 minutes. Without sharing, it will cost 20 minutes in total to answer these two queries. However, in practice, we can utilize analysis results of frames between 15 minutes and 20 minutes to answer these two query requests, which can help us reduce the processing pipeline time of the second request to 5 minutes. We call this relationship between two queries spatial sharing. In the last example, U1 submits a Q1 request at time t1 to the system, and U2 submits a Q2 request simultaneously. In prior works, these two queries must be processed separately. Suppose that each request requires 10 minutes to be analyzed, and it costs 20 minutes in total. We find that there is a logical relationship between these two queries. For example, if we want to find all frames satisfied with Q2's requirement, there must be at least one person in them. Hence, Q1 can work as a preceding filter of Q2, which can help reduce the total number of frames to be processed. Existing works reveal that the target frames only occupy a small part in many real-world cases. Hence, it is valuable in practice. We call this relationship as logical sharing. Compared with prior works, we focus on optimizing the processing performance of multiple video queries. The key observation of this paper is that a sharing-based optimization method, including temporal sharing, spatial sharing, and logical sharing, can help improve systems' overall performance. In this paper, we propose DVQShare, an analytic system for DNN-based video queries. The key idea behind this system is sharing. There are three main design ideas. First, we can cache historical results to accelerate the processing of future queries. Second, we can reuse analysis results for the same video clip to reduce the total amount of frames to be analyzed. Third, results produced by one query can be logically reused by another query. The proposed DVQShare system composes of two main components. Queries received are processed in the batch manner. In the analysis module, a query queue is responsible for receiving query requests from users. The query analysis submodule is used to process the query pipeline configuration according to the BIOS-free sharing relationships. The execution module will first take the output of the analysis module as input and generate the corresponding processing pipeline with the query pipeline generator. Then all pipelines generated will be instantiated and processed in the query pipeline execution component. In this paper, our prototype implementation is based on the MSNet framework. but it can be extended to support other frameworks such as TensorFlow, PyTorch, and TensorRT. Next, let's get right to the design ideas of the DVQShare system. The first one is based on temporal sharing. In a real-world situation, a video analytic system often needs to process similar queries from multiple users at different times. For example, user A may submit a request to check the traffic flow of a nearby intersection to plan his route to work. A government office B may submit the same request to the system to help them control traffic in the future. Hence, a historical store is used to catch results to help improve the processing performance. The second design idea is spatial sharing. The corresponding insight is that multiple queries may have interest in the same video clip. Think about the following example. User A might want to check the traffic flow between 10 a.m. and 11:30 a.m. Meanwhile, another user B may query the traffic flow ranging from 11 a.m. to 12 a.m. In practice, we can merge the above two queries into a single query. Results of frames ranging from 11 a.m. to 11:30 can be shared to reduce the total amount of frames to be processed. Compared with the above two design ideas, the logical sharing is a little more complicated. What do we mean by logical sharing? The insight is that analysis results can be logically used across multiple queries. How to determine whether two queries can share results logically is the key problem to be solved. In this paper, 3 kinds of logical sharing relationships are considered. The first one is that we can reuse results across multiple queries if the query targets have a semantic relationship. The idea is inspired by the design of ILO 9000 model. In this example, user A's query target is vehicle, a hypernym of user B's query target car. Thus, we can use the output of user A's query as a filter in the processing of user B's query. As discussed above, multiple model candidates can be used to answer the same query request, but they are often trained with different accuracies. In the following example, user A chose UAV3 to count the number of vehicles, and user B tends to use a more accurate model, first RCN, to do the same work. Similar to no-scope, we can use the results of user A's request as a filter to pull away frames without the target object when processing user B's request. Conversely, we can also directly reuse results of user B's request to answer user A if the corresponding results have been cached. At last, we can utilize outputs from a limited query to accelerate the processing of a recognition query. As shown in this example, user A's query results can be exploited to filter out frames without people in them. The system only needs to process frames left to recognize the query target. Donald Trump. We use the same queries shown above before to show how the DVQShare system works. With the existing systems, 2 separate processing pipelines will be instantiated for Q1 and Q2 before processing. Then the system launches these 2 pipelines separately to obtain the corresponding results. Unlike existing systems, DVQShare can export sharing relationships between Q1 and Q2 to optimize the generation of processing pipelines. As analyzed above, outputs of Q1 can act as a filter of Q2. Hence, DVQShare will combine these 2 processing pipelines into one single pipeline. Q1's output works as a gate to control, whether the current frame should be analyzed by Q2's processing pipeline. The proposed optimization strategy can also help eliminate the video decoding cost in Q2's pipeline. At last, we implement a prototype based on MSNet, which is a popular deep learning framework. 3 video data are considered in this paper. 2 of them are from existing works, such as NoScope and Basic. Friends is a short clip from a television sitcom. Further, we conduct experiments on the above videos with 8 queries and 5 candidate models. The corresponding accuracies are listed as follows. In order to explain the experiment results, we present an auxiliary notation, ROLAP, which is defined as the ratio of the length of the overlap video clip to that of the second query's target video clip. Details about the tested video data and the configurations of all 8 queries are listed in this table. First, as shown in this picture, the performance benefit of temporal sharing is obvious. When the overlap ratio is 1, DVQShare can help achieve about 100% performance improvement in all 8 queries. Next, with spatial sharing, we can get a speed-up ratio up to 2 when the overlap ratio is 1. In order to evaluate the performance with logical sharing, we conduct 3 experiments. First, we choose 2 query groups from the above 8 queries, and query targets of 2 queries within each group have a semantic relationship. From this picture, we can see that the processing performance is small or even worse than the baseline implementation. By inspecting Q4's and Q6 outputs, we find that almost all frames in the target video clip are returned. It means that the number of frames to be drafted is limited. In this situation, DVQShare works like a traditional analytic system. However, as shown in existing works, anomalous senses generally appear rarely in many real-life cases. We conduct another experiment with a synthetic video clip. The number of frames returned by Q4 and Q6 to the total number of frames is fixed at 20%. As shown in the right picture, DVQShare can achieve up to 2 speed up when the overlap ratio is 1, which means that the proposed system can be still helpful in many real-world cases. Then, we evaluate DVQShare's performance when processing queries configured with different models. The corresponding results show that it can achieve up to 33 performance improvement in this experiment. Then we evaluate DVQShare's performance. Further, we evaluate the proposed system with semantically related queries. We can see that it can achieve about 17% performance improvement when the overlap ratio is 1. So, we have proliferation of camera devices and DNN-based video analytic applications. An analytic system needs to process multiple count queries at most time. The key observation of this paper is that sharing results across queries can help us improve the overall performance. By analyzing existing queries, we found that there are 3 types of sharing relationships: temporal sharing, spatial sharing, and logical sharing. And the main contribution of this paper is that we propose a new video analytic system that can accelerate the processing of multiple queries by exploiting these 3 sharing relationships. experimental results show that the performance improvement that can be achieved is proportional to the overlap ratio and is in inverse proportion to the ratio of the number of query target frames to the total number of frames. Thanks for your listening. If you have any questions about this paper, please feel free to email me.